Hello. Today we're going to talk about end milling, but tool basics. Some of this we've looked at before break, but it's been a while, and so we're going to take another look at it real quick. So one of the things we want to talk about are some of the different common cutting tools that you might use. We talked a little bit about that high-speed steel is the ones that we have in our shop or in our classroom. But there are a lot of different types, different materials that you can make tools out of. So there's a list of some really common ones. There's a lot more out there than just these, but these are some of the more common ones that you might run into. Again, high-speed steel is a really, really common one. It's usually one of the cheaper options. Some of the other ones, the cobalt and the carbide, are used for generally harder materials. We don't really cut anything very hard in our class, but if you're getting into steel or maybe titanium, or you're getting into any kind of harder material, you're going to want something that's a little bit better than the high-speed steel for a lot of that. And so cobalt is a kind of a lower option as far as cost compared to the carbide. But carbide is a very, very good cutting option. It cuts really well. However, the problem that carbide tools tend to have is A, they're expensive, and B, they tend to be a little bit more brittle. So they tend to shatter a little bit. Not necessarily like the whole tool breaking, but just the edges or the cutting edge will break off. Instead of wearing down and needing to be sharpened, they'll just chip away. And so that's the problem that you see with those. But they're definitely good for cutting heavier, again, harder materials, denser materials. The powdered metal cobalt is kind of a in-between option between this carbide, which again is more expensive and a little bit more brittle and fragile. So it kind of is the lower cost option of maybe a carbide tool. The last one on the list, that carbide tipped ones, those are actually ones that are not carbide as a whole, but just they have carbide ends on them on the actual cutting surface. And so those are a kind of a cheaper option than some of the solid carbide. You also see those a lot in like facing mills and things like that, where you have tools that you can add on. And so they have carbide tool tips to make the actual cut. But then the rest of the body is something else like high-speed steel. All right, different end mill types. We've looked at a lot of these earlier, but just going to quick run through them again. Square end mills, those are the most common. We use those pretty much exclusively in the stuff that we do. They're very good general purpose cutting mills. You can do all different types of things with them. And then there's the ball end mill and the corner radius or the bull nose. Those are very similar. Those are for cutting things where you want some contour. And so you want a nice, smooth, curved surface. You're going to use those. That's not necessarily horizontally curved. So, if it's a horizontal, like a pocket that's got curve to it, we'll still probably use a square end mill for that. But if you want kind of a dome shape or something that's got a curve to it, that's going to be, more three-dimensional, that's when you start seeing those end mills like that. Then you have the tapered ones. Tapered ones you usually use more for engraving, but they do have the nice property of they cut a little bit better than some of the other ones as far as you're going to get a more even cut all along the cutting edge than maybe you do on some of the other ones. But generally, they're going to be used more for engraving or fine detail work, where you're just cutting a little bit at a time and not necessarily roughing materials out. So we talk about roughing end mills. Roughing end mill just means that you're going to cut a lot of material really quickly. And so we'll use those generally to kind of do the majority of your cutting, and then you finish up with the finishing mill. Other mill types, we're not going to get into these too much because we don't use these, but there are some different profiles that you might see out there. Some of these are used more with 4-axis machines or 5-axis machines, where you can turn the actual plate that's holding your part down, so you can actually get more control over your cutting. The lollipop is one that definitely gets used in that. If you watch some videos on YouTube, you'll definitely see that used when they use those 4-axis, 5-axis type mills. T-slot's really nice because you can cut undercuts that we can't normally do with a 3-axis mill, because we can only come in directly from the top. We can't cut underneath. If you had something that needs like a little lip on it, we really can't cut that without turning the part on its side. And sometimes you just can't get to those. So a T-slot mill is a really nice option. And there's some other options besides T-slot that can do the same sort of thing. Face mill, we talked about those before. Facing mill is just going to use to cut a smooth top surface on something. And so there's lots of different types of facing mills. But again, that's just going to Basically just cut a real smooth, even surface on top of whatever material, whatever parts you're making. And then the slot drill, as the name would imply, is going to be used to make slots and whatever parts you're making. So if you wanted to cut a slot out, you'd use a slot drill. We don't really have any of these in our repertoire, but they're out there. All right, we talked about flutes before as well. I'm just going to do a real quick overview. Just a reminder, we have 4 flute mills. We do have 1-2 flute, but that's the only one we have. But the difference between them is that the less flutes you have, the less cutting surfaces you have, the more material you can cut per pass. As you spin that around, you've got more space available. The more flutes or cutting surfaces you add, you're getting smaller and smaller openings for material to be ejected out, to evacuate out. So generally use the lesser flutes if you're going to cut a lot of material quickly, but generally they don't work as well with harder materials. And then you use the larger number of flutes, the 4, the 6, the 8, if you're cutting hard materials where you're taking really small chunks out as you cut. So you don't want to cut a lot of material, but you just want to be able to cut out a little bit faster. Generally, the more flutes you have, the cleaner the cut's going to be. So the 2 and the 3 are not going to cut as cleanly, but they're going to cut a lot faster. And then we talked about the difference between center cutting and non-center cutting. Again, center cutting is just a little more general purpose. It can do a lot of things. So you kind of do a lot of different types of operations, whether it be pocketing and side cutting, those sorts of things, but also it can do the plunge cut, which is basically what a drill would do, is come straight down into the material. Whereas a non-center cutting, you can't do some of those things. All you really can use it for is side cutting. So anything where you can approach the material from the side and make your cut, non-center cutting drill bit is going to work well for that. And there's a lot of those out there, a lot of operations out there where that's really useful. And the non-center cutting we talked about before are quite a bit cheaper and easier to produce for the company that's making these tools. So you do see them, and they are widely used. They're just not going to be as all-purpose as maybe a center cutting mill would be. We don't have any of the non-center cutting because we really need our stuff to be general purpose. We don't want to have all these specialty type tools. So we have the center cutting. One other thing that you can do is you can have lots of different surface coats that you can put on these. So besides using different actual materials for the bits themselves, you can also put surface treatments on them. Basically, it's just like an outer coating on the bit. And so there's 3 different ones that include titanium here on ours. Now there's a ton of different options out here. These are by far not all of them, but so these are some pretty common ones. So all the ones with titanium are really high strength. They're good for cutting very hard materials. You kind of get different properties depending on which ones you use. So like the titanium nitride and the titanium carbonitride, those are very similar. The second one, the carbonitride, is going to be a little bit better for cutting harder materials than the first one, the nitride one, but they both are pretty similar. The aluminum nitride, that one is actually good for really high temperature things. So if you're cutting a high temperature where you're going to get a lot of heat generated as you're making a cut, that one's a little bit better for that high temperature situation. It's not going to get gummed up or lose its edge quite as easily. The last one on here, this zirconium nitride, that one is really good for non-ferrous materials. So anything that's not basically iron based. So you're looking at aluminum, brass, copper, things like that. This one's really good for those types of materials. Leaves really nice finish. And so there's a lot more out there than just these, but these are some pretty common ones. All right, so a couple of things you want to be thinking about when you start looking at making a selection as to what you're going to use to cut. When you're choosing which tools you want to use, we're going to look at the most important ones here. Is that first off, you always want to make your end mill as short as possible. And again, it's just about rigidity. You want to basically, you don't want vibration. One of the big problems with drill presses is there's usually too much vibration within the cutting head as you're doing that drill bit down in there. And so you don't get good dimensional tolerance. And so that's why we want with the mill, we want everything to be as rigid and solid as we can. And so the shorter the end mill, the less vibration you're going to get, the less dimensional tolerance problem, because it's not going to vibrate as much. And so you're going to get things a little more accurate. We talked about it earlier, 2 or 3 flutes are good for removing lots of material. So when you're doing that first roughing operation, you want to cut a lot of material away. you're going to use 2 or 3 flute type stuff, and then you go to those higher numbers, the 4 or 5, 6 flute type things, when you want to cut kind of a finish, because it's going to get a better finish surface when you use those higher number of flutes. Cuts less material, but it's going to look better. You also want to use your largest diameter. So whenever you're cutting, if I could do the same job with a, say, 1/4 inch versus an 1/8 inch, I'm going to want to pick that 1/4 inch, because it's, again, going to have less vibration. It's going to be more structurally sound. And so you're going to get a better dimensional tolerance. It's going to be more accurate cut that way, because it's not going to vibrate as much. And so that's what we want. We always want to use the largest tool that we can for whatever job we're doing. Some jobs you just have to use small tools, but if you can use a bigger one, that's what you're going to use. The last 2 things, we kind of already talked about these, that, you want to use those tools that match what you're needing job-wise. So, if you need carbide because of the material you're using, then you're going to want to use carbide. If you need some of those coatings, you're going to use those. Those are all just kind of considerations that you make as you're purchasing tools and looking at, what am I doing versus what do I need to purchase for that. All right, last little bit here is just a quick reminder of some formulas. These formulas are actually the same formulas we looked at with speed and feeds, except they are putting them in a little different format. This is probably more realistic as far as what you'd see as a machinist. So this first one, this RPM, that's just spindle speed. We had our spindle speed formula. That's what this is. But they're putting it as RPM. And then that surface feet per minute, that was that number we looked up on the chart. And we said, you look up on the chart and find the value for aluminum or steel or whatever it was. And then we multiply that by 12 and divided by the circumference. Well, here they're basically taking the 12 and the pi from the circumference measurement and combining them into one number. They basically took 12 divided by pi, and that's where they're getting this 3.82. And that way, the denominator of this will just be the diameter instead of being circumference. But it's still the same formula. It's just, again, a little bit simpler. They don't have pi in there, so it just looks a little bit easier if you're not as comfortable with the math. And so it's a little bit easier formula for people to use. Same thing for this. This is our feed rate formula, and it's, again, not any different than what we looked at. It just looks different because we're using different terminology. But inches per minute, that's our feed rate. And it's our spindle speed, or RPMs, which, if you remember in our formula, we had that RPM value as our spindle speed times the number of flutes. So again, that was in that formula we saw for speed and feeds. And then chip load is a different term than what we use, but we had that value that we looked up that was the tooth count, or the tooth feed that we were looking at, that, again, we pulled off of a chart. That's what that chip load is. And it's just kind of giving us an idea of how big the chip is going to be when we're cutting. And again, chip is the little waste product that you're getting as you're cutting. And that's one of the things machinists look at. If you talk to somebody who's machined a lot, they'll talk about the chip load, or really they're looking to talk about the size of the chip. And that's how a lot of the old time guys that do this on their own, that's how they tell if they're getting a good cut or not. To look at the chips and say, oh, that looks like a good size, or it's too small, or it's too big, and I'm cutting too fast, or I'm cutting too slow, that kind of thing. These last 2 equations are the same as these first 2. They're just solved for different variables. So this one is the same as the second one. We're just solving for the chip load. And so if you were trying to figure out what the chip load was, and you're kind of working your own way through this, you can figure out, okay, if I run it this inch per minute with this RPM, with this number of flutes, this is what my chip load should be. This would be where, if you're experienced and you're trying to determine what those values in the chart should be, this is kind of how you would do that. But you'd have to have a lot of experience in what you're doing, so you kind of know if that makes sense or not. And for us, that's not something we're going to do. We're just going to look it up in the chart. Same thing with this one, our surface feet per minute. Again, that's the number we're looking up off the chart, but you can work it this way. If you know what you're doing, you can kind of figure out what RPM do I need to run this at for this tool diameter to figure out what that surface feet per minute is. But again, it's kind of backwards of what we do. We're going to look up that surface feet per minute value. We're not going to calculate it this way. All right, that's just a quick run through of everything we've done. I'm going to close off here, but we'll have some more videos about G-code and milling in general. So we'll talk to you later.